Okay, so in section 4.2, we're going to start talking about a concept called logarithms. I don't expect you to be as comfortable and confident with logarithms as you were with exponents, but I will say the better you understand exponents, the easier logarithms are to make the jump to, okay? So before I show you what a logarithm is, let's remind ourselves what an inverse was. This is all the way back on test 1. Inverses are, remember, opposite functions that undo each other. The other thing about inverses, remember, is that x and y are swapped. So all the x's become y's, all the y's become x's. So here is an exponential function that we just got finished looking at, y equals b to the x power, okay? So this was the same type of function we discussed in 4.1. So what if I asked you to find the inverse of that guy? Okay, what did I say we do with x and y if we want the inverse? We flip them, right? So the inverse would be x equals b to the y power. Okay, so think of this like this is the inverse of an exponential function. But the problem with this is normally when we did inverses before, remember we would then solve for y. What's going to be the problem with us trying to solve for y here? Where's y located at? In the exponent, and that's kind of at an untouchable location as it is. And so we're going to look at a new form for the inverse called a logarithm. Okay, so it's going to be the same as saying y equals log base b of x. Make sure when you write it that the b is tiny, like b should be like exponent size. So this is what we call a logarithmic function, but that's just a fancy way to say a logarithm. So once you learn that logarithms are just fancy exponents, I promise this is not going to be too difficult, but until you can get as comfortable, or at least maybe half as comfortable with logarithms as you are with exponents, they're going to seem a little strange. So logarithms are simply just another way to write the inverse of an exponential function. They're also the way that we, quote, undo exponential functions. So remember how addition and subtraction undo each other, how multiplication and division undo each other. Well, logarithms are going to undo exponents. Okay. So I just want us to kind of get our feet wet with kind of what goes where. Okay. So before I talk about this, notice that the base here, so before you write anything else, right, the base here becomes the base over here, right? Notice that the exponent here becomes the answer here, right? And then the x value here becomes what we're taking the log of here. So you really just have like 3 numbers slash letters and you have to know where they go, right? So let's practice that kind of back and forth. So first, I want you to take a log form problem and switch it back to exponential form. And then maybe we'll do the other way too. So here is a logarithmic expression that is something that's true, that works out. So I don't think there's any shocker here, right? This is logarithmic form. So you just need to learn what goes where. Okay, so we're going to rewrite this to be what we're more comfortable with, right? And there's no question that we're more comfortable with exponents, right? So notice the order that I'm about to write these. Okay, so the base becomes the base. Notice the base of the logarithm is now the base of the exponent. Okay, the answer to the logarithm is always the exponent in exponential form. and then the other number goes here. Notice that's the only way these numbers combine and make it true, right? 2 to the third power is actually 8. 2 times 2 times 2. 2 times itself 3 times. So this would be exponential form. So if you kind of know what things are called, I think you get the base for free because the base here becomes the base over here. So it's really just knowing where the other two things go, right? And once you figure the second thing, frankly, it's just kind of by default where the third one would need to go. All right, so let's see if we can go backwards. So let's say I'm going to give you something in exponential form and I want you to write it in logarithmic form. So before you even try to tackle the homework, you need to pay really close attention to these first two examples we're doing today to make sure you know kind of what goes where, because it's kind of like a puzzle. So notice, no surprise, right? 4 squared is 16, right? That's true. 4 times 4 is 16. Okay, so this is, of course, what kind of form? This is exponential form. So I'm asking you to rewrite this in a different form, but put things where they go, right? So I'm going to do the easy part. It is going to be the log base 4, because the base here is 4, so the base of a log becomes 4. And then do y'all remember what to do now? Where's the exponent supposed to go in a logarithm? I'm going to skip some space. It's supposed to be the answer, right? And so then by default, the 16 has to go here. Okay, so notice the 4 is pretty obvious. It's just the 16 and the 2, you have to figure out which format they go in. And so if you've never really covered logarithms before, that's okay. You just need to kind of quickly learn where things go, essentially. But what that rewrite step, once you get the hang of it, allows for you to do is take things that are maybe in an uncomfortable form and try to rewrite it. So let's say I asked you to solve the log base 5 of x equals 2. So I would look at that and I would be like, I don't really prefer this logarithm form, so I'm going to immediately change it to the form I'm more comfortable with, which is what? Exponential form. All I have to do is figure out what goes where. Okay, so I'm going to do the one that's easy. The 5 base becomes the 5 base of the exponent. Okay. What happens to the answer to the logarithm? Where do we put that when we switch it to exponential form? So the 2 becomes the what? The 2 becomes the exponent. Sorry, I'm kind of giving you the answer already. And then the x value just goes in the other spot. So we should be able to solve this now, right? Because what is 5 squared, of course? 25. So we're going to take a break and look at some rules, but here is something that I probably will have you write down more than once. The answer to a logarithmic expression or a logarithm problem, if you want to say it like that, is basically what exponent you need to raise the base to get the other number. So the answer to a logarithmic expression is always looking for the exponent. Okay, it's asking you what power do I need to raise that base to give me the answer that I'm looking for. Notice that's what it was here, right? What power was I raising the 5 to? I was raising it to the 2 power because that was the answer to the logarithmic expression. Okay, so we are going to review a little bit further the rules of exponents that I just mentioned, but we're going to do it with some examples. So we already kind of wrote this today, so I'm going to write it briefly, but I really want to get to some examples. So remember, the product rule said, I'm going to write it a little bit differently than what I had before. X to the a power times x to the b power would be x to the a plus b power. So notice before I think I listed them as b for base, but this time I'm listing them as x's. Same difference, same rule. So here's the gist of the rule. When multiplying terms with exponents, add the exponents. I don't want to get really wordy with this. The bases do have to be the same. So that's kind of a given. So when multiplying terms with exponents, as long as it has the same base, you're going to add the exponents. So let's look at some examples with maybe some varied difficulty. So we're used to problems like this before now, where I say combine x to the third times x to the fifth. So what would that obviously be? X to the eighth, right? So we would add the 5 plus the 3, and we would get x to the eighth. But that same rule applies if you have an exponential function, or maybe something where you have a base other than x. So notice this is 3 to the 7th times 3 to the 8th. It's the same exact rule as I had before. Okay. Notice what we are not going to do is do 3 times 3, because we're not supposed to do multiplication until we handle what part first? Exponents first, right? So notice the base isn't going to change. All we're going to do is do what with the exponents? Add them. Okay, I'm not going to punch that in my calculator, by the way, because that would be a really crazy big number, because that would be 3 times itself how many times? 15 times, right? So that would just be super, super large. But even if you have, I'm going to put a star by this one, even if you have something weird, like 2 to the x power times 2 to the 3x power, the power or product rule, still applies here. Notice the bases are still the same. So what are you supposed to do with those exponents, just like you did for the previous two examples? Just add them. So this would be 2 to the x plus 3x power. And what is x plus another 3x? 1x plus 3x would be how many? 4x. Okay. So notice we're taking old rules and just applying them to new types of problems. All right, so let's look a little further at the quotient rule. So I know we already briefly talked about that too, back in the exponential section. So remember this, what did we do with the exponents again? Subtract them. So the explanation of this is when dividing terms with exponents, again, make sure the exponents are the bases are the same. But when dividing terms with exponents, you subtract the exponents. So kind of like we did on the first one, let's do some examples of kind of some varied difficulty. So if you have x cubed over x to the fifth, notice the bases are the same, so I'm going to subtract those exponents. So this is going to be x to the 3 minus 5 power, which is x to the negative 2. Okay, if you're still not comfortable with negative exponents, you need to review that, because you're going to need to get more comfortable with them. This is the same as 1 over x squared, and in fact, that's how I would want you to write that answer. I would not want you to leave it as x to the negative 2 power. It's 1 over x to the positive power, whatever it happens to be. Remember, negative exponents create fractions. So what if you had this? So notice instead of x's, now I have numbers for bases, right? But notice that I can still use the quotient rule because the bases are the same. They're both 4. So I'm going to do the same thing that I was doing before. I'm going to keep the base the same, and what am I going to do with the 5 and the 2? Subtract them. So it would just be 4 cubed, which I probably could go ahead and work that one out, right? I didn't do it here because it would have been crazy big, but 4 cubed is not bad, right? 4 times 4 times 4 would be 64. Okay, so when you can write something nicer, we'll try to. But what I want us to be able to transition to is how do you solve weirder ones like this? Okay, so notice definitely still quotient rule, right? We're still dividing. The bases are still the same. So what am I going to do with those exponents just like I have been? The base is going to stay 3, and what am I going to do with the 3x and the 4x? Subtract them, right? Notice it's always top minus bottom. So I end up getting 3 to the negative x power, which is the same as saying 1 over 3 to the x power, because negative exponents create what? Fractions. Okay, we really have to know that. So just like you wouldn't give an answer as 2/4 when you could reduce it to a half, I don't want you to leave an answer with a negative exponent. It's not considered simplified, so I want you to rewrite it as a fraction. And then lastly, we'll talk about this one a little more in depth, the power rule. So this is for when you have a power raised to another power. So what did I tell you to do with the exponents? Multiply them, so just be x to the AB power. So the everyday explanation of this is when raising an exponential term, so it's already an exponent to another power. So it's like something squared or something like that, and then you raise it to a power again. You're going to multiply the exponents. So let's just do a couple examples of this one. So the old school version might look something like this. X cubed, but then to the 4th. So I would do what with those exponents? Multiply them, so it would just be x to the 12th. But also make sure you can handle weirder things, like what if it's 3 to the x power, but then raised to the negative 2 power? So notice it's still an exponent being raised to another exponent. So what do I want you to do with those exponents? Yeah, so I want you to say 3 and then to the x times negative 2. So that's a multiplication dot. But yeah, you're exactly right. It'd be 3 to the negative 2x. So that'd be almost right, but why wouldn't I like you to leave it like this? Because it's a negative exponent, right? So it would be 1 over 3 to the 2x. Okay, so next time we're going to look at some logarithms that use maybe some of these more unusual exponent rules here. So just be ready to kind of continue on with this next time.